Hello students, welcome once again in my video lecture. Dear students, myself Ravindra Budwan sir from Sri Tilok Jain Higher Secondary Vidyalaya Pathradi. In this program of video lectures, we started with this chapter from 11th chemistry, that is adsorption and colloids. We have studied many subtopics in my previous videos. Now in this video we are going to study the important features of solid catalysts. So as we know, solid catalysis means the catalyst in this process is in solid state and the reactants may be in liquid state or in gaseous state. So what are the features of this catalysis, how they are affected by different factors, so that is described in this topic. The first feature is catalytic activity. So first feature is catalytic activity of the catalyst. Catalytic activity depends upon strength of chemisorption. Now we know chemisorption means the adsorption in which the chemical forces, that is chemical bonds, are formed in between adsorbent and adsorbate. So in case of the catalytic activity, this depends upon the strength of chemisorption. More the strength of chemisorption is there, more is the catalytic activity. So how strongly the chemical bonds are formed in between the adsorbent and adsorbate decides the catalytic activity of the catalyst. Then active catalyst, that catalyst is said to be active which adsorbs the adsorbate molecules strongly. That is, when reactant molecules, may be gas or liquid, may be in the gaseous state or liquid state, strongly get adsorbed on solid catalyst. That means when reactant molecules, that is adsorbate molecules in the process, if they strongly get adsorbed on the surface of the catalyst, that is adsorbent, then we say that catalyst is active catalyst. Here some examples are given. For example, elements iron, that is metal, then vanadium, chromium, they are strongly adsorbed. The metals like iron, vanadium, chromium, they strongly adsorb the different gases on their surfaces, such as oxygen, O2 gas, then acetylene gas, C2H2, then ethylene gas, C2H4, carbon monoxide, CO, H2, dihydrogen, then carbon dioxide, CO2, or dinitrogen, that is N2 gas. So these gases get adsorbed easily and strongly on the surfaces of these metal catalysts like iron, vanadium, chromium, etc., which are D block elements. Then manganese and copper, they are unable to adsorb nitrogen gas and carbon dioxide gas. So here we see the difference in between different metals. Iron, vanadium, chromium, they are able to adsorb these gases strongly, whereas manganese and copper are not able to adsorb these gases. They are unable to adsorb dinitrogen and carbon dioxide gas. The metals magnesium and lithium, they adsorb oxygen selectively. So oxygen is adsorbed on the surface of magnesium and lithium only. So they adsorb oxygen gas selectively. They do not adsorb the other gases on their surfaces. So here we can say that the catalytic activity of different elements, that is different metals, is different towards different gases or different reactant molecules. Then second important feature of solid catalysis is catalytic selectivity. Now we studied the first factor or first feature, that is catalytic activity. Now catalytic selectivity, catalysts are very selective towards the reactants or the adsorbate molecules. Some solid catalysts are selective in their action. So whatever the catalysts are selective, they are highly selective. That means solid catalysts, they adsorb the reactant molecules selectively. They adsorb the particular molecules only. they do not adsorb all molecules randomly, but they adsorb the selective molecules, so they are said to be selective in their action. So what is the concept here? Same gaseous reactants produce different products when different catalysts are used. That means the reactants are same. Let's say gaseous reactants, they are same, but they produce the different products when catalysts are used different. That is, the product will depend upon the catalyst and not on the reactants. So reactants are same, but the products are different with different catalysts. Examples are given here. Two examples are given. First example, ethylene gas C2H4, ethylene plus oxygen dioxygen molecule O2 oxygen gas in presence of the catalyst palladium and alumina. Palladium metal and alumina, we get the product acetaldehyde, that is ethanol, CH3CHO. It is aldehyde. 2 moles of acetaldehyde are formed in the gaseous state, whereas the same reactants, ethylene gas plus O2 oxygen gas in presence of silver and alumina, Ag and alumina, we get ethylene oxide C2H4O as the product. So ethylene oxide is formed here. So different products, acetaldehyde and ethylene oxide, are formed with the different catalysts, that is palladium alumina and silver alumina respectively, where the reactants are same, ethylene gas and oxygen gas. Second example is carbon monoxide in the gaseous state plus 3 moles of H2 dihydrogen gas. In presence of the catalyst nickel, we get methane plus water, methane gas plus water vapors, that is in the gaseous state. The same reactants, carbon monoxide and 2 moles of H2, that is dihydrogen gas, in presence of the catalyst copper, zinc oxide and chromic oxide Cr2O3, we get the product methanol, CH3OH, methanol. Here also the products are different, that is methane plus water and methanol with the different catalysts nickel and copper, zinc oxide and Cr2O3 respectively, even though the reactants are same, carbon monoxide and dihydrogen gas. So it is known as catalytic selectivity because the products are formed according to the catalyst. The third feature of solid catalysis, it is shape selective catalysis by zeolites. So shape selective catalysis by zeolite. Now here the catalysis depends upon shape. So zeolites, now what do you mean by zeolites? Zeolites are aluminosilicates with 3-dimensional network of silicates. Now we know silicates, SiO2 network of silicate, SiO2. So aluminosilicates, that means aluminum atoms are inserted in between the silicate network here. So in this network, some silicon atoms are replaced. Some silicon atoms are replaced by aluminum atoms, giving ALOSI framework. See here, from SiO2, this aluminum atom has replaced one silicon atom. So ALOSI, this type of framework is formed in the network of the silicate. So we say that this is the aluminosilicate. So when aluminum replaces silicon atoms in the silicate network, then it is called as aluminosilicate, and that is nothing but zeolites. So it forms microporous structure. So zeolites are replacement of silicon atoms by aluminum atoms. It forms microporous structure. Micro means very small and porous means having smaller vacant spaces in between the structure. So it forms microporous structure. Hence reactions in zeolites depend upon size and shape of reactants. If these zeolites act as the catalyst, then the catalysis or catalytic activity of this zeolite, it will depend upon size and shape of the reactants, as well as the products formed, as well as the pores, cavities of the zeolites. So what factors are responsible here? The size of the pores and cavities in the zeolites, then reactants, their size and shape, and the products formed. Here, whatever the size of the pores and cavities of the zeolites is there, the reactants as well as product, these molecules should accommodate into those pores and cavities of the zeolites. So they should have the size and shape according to the pores and cavities of the zeolites. Therefore, it is selective. Therefore, zeolites are shape selective catalysts. So we say that the zeolites are shape selective catalysts. Example is given here in petroleum industry. Zeolite catalyst convert alcohols directly to gasoline, that is petrol, by dehydration, which gives a mixture of hydrocarbons. So by dehydration, removal of water molecule, the alcohols are converted to gasoline, that is petroleum products, petrol, by dehydration, and giving the mixture of different hydrocarbons in the petroleum industry. This is the example of shape selective catalysis by zeolites. So students, we shall stop here in this video. You see my further upcoming videos to study the different important topics from chemistry. Thank you very much.